Hey everybody, welcome back. Thanks for watching. So it's been a while, so I think we should do this neat little integral here. So we've got the integral from 0 to 1 of the square root of e to the x over the square root of e to the x plus e to the minus x dx. So let's see what we can do here. So the first thing I'm thinking about is let's write this as the integral of a single square root. Let's see if that's helpful. Give myself a little space here. And so maybe initially it doesn't seem so helpful, but I'd really like to get rid of this e to the minus x business right here, right? So I'd like to get rid of this. Let's multiply the top and the bottom by e to the x. Okay, so that's going to help quite a bit here. And let's see what we have here. So of course, adding exponents when we multiply the same base gives us the following. So it looks like e to the 2x and then over e to the 2x plus 1, right? Because e to the 0, of course, is 1. Okay, that's all under one single square root. Okay, so I know we can take square roots over fractions. So let's try that. So this will be the square root of e to the 2x, which is just e to the x. And then down here, it looks like we can write this e to the 2x as e to the x squared. That seems just fine. Plus 1. And then dx. Okay, so everything seems pretty good so far, and it looks like we have a nice substitution. So let's let u equal e to the x, and then compute the derivative here. So du is exactly e to the x dx, and then I'll also change the bounds. Okay, so that's nice. So that's going to give me exactly du, or 1 du. And then here, I've got the square root of u squared plus 1. And then for bounds, okay, so x goes in for x. That'll be e to the 0, which is 1. And then here, x goes in for x. And so e to the 1 is just e. And this reminds me of a trig substitution, sort of Calc 2 style. And specifically reminds me of a tangent substitution. So let's dive in to that. So let's say that u is equal to a, or 1 in this case, tan theta. So I'm switching variables again, and I'm hoping that the trig substitution introduces a Pythagorean identity that'll collapse down the radical. That's ultimately the goal here. And so du is secant squared of theta, d theta. And of course, we're going to need corresponding new bounds. Okay, so let's see here. For the new bounds, let's see. If u is equal to 1, then tangent of theta. That implies that theta must be pi over 4. And if u is equal to e, then theta must be the inverse tangent of e. So let's go ahead and note that. So we have the following. Okay, so again, new lower bound of pi over 4, because, just one more time, if 1 goes in for u, then theta must be pi over 4. And then for my upper bound, if e goes in for u, then theta must be the arctan or inverse tan of e. Okay, so that seems nice here. So just continuing with our substitution, we have the following. So du is exactly this quantity. So that's secant squared of theta, d theta. And then downstairs, we have the following. So u we said was tangent, so inside the radical, we'll have tangent squared of theta plus 1. But that's a classic Pythagorean identity, right? Tangent squared of theta plus 1 is secant squared of theta. So that gives us the following. So we've got the integral from pi over 4 to the arctan of e of, looks like secant squared of theta over the square root of secant squared of theta, d theta, again by that nice Pythagorean identity. And so on this interval, I don't have to worry about absolute values. So that'll be secant, which will cancel out with a factor of secant here. And so it looks like we've got the integral from pi over 4 to the arctan of e of secant of theta d theta. Okay, so that's pretty nice. We've got a classic result here. And so we have the following. So we have the natural log of the absolute value of secant of theta plus tangent of theta. From pi over 4 to the arctan of e. And so we'll just continue through with the fundamental theorem of calculus. And so we've got the following. So we've got the natural log of the secant of the arctan of e, we'll take care of that in a moment, minus, well, the tangent of the arctangent of e. Tangent and arctan are inverse functions, so that will give me an e. So that seems nice. And then, of course, minus by the fundamental theorem. So we've got the natural log of secant of pi over 4, but that's a classic value, plus the tangent of pi over 4, another classic value. Oh, this should be a plus, it looks like, right? Because we've got secant of theta plus tangent of theta. So that's a plus. That's nice and fixed there. I bet you noticed that. And then here, let's take care of this, and then we'll collapse this down a bit more. So we've got the natural log of the absolute value of the secant of the arctan of e plus e minus the natural log of radical 2 plus 1. And so, yeah, let's do a little bit of side work here, right? So let's take care of this. So, how about we say the following? Let's do this. How about we say, let's let alpha equal the arctangent of e. So by properties of inverses, we can rewrite this, right? So we know that the tangent of alpha equals e. And we can put that over 1 and make a right triangle. So here's angle alpha. And tangent is equal to opposite over adjacent. And so the Pythagorean theorem yields the following for the hypotenuse. This is the square root of e squared plus 1 squared. And that's really good because now we're in a position to take the secant of alpha, right? We said this was alpha. So if we do that, we get the following. So secant, that's just the flip of cosine. So the secant of alpha would be hypotenuse over adjacent. So that's nice. And from before we have this plus e. We could also make the observation that this quantity is positive, so we don't need absolute values. And so by properties of logarithms, right, the difference in logs is the log of a quotient, we have the following. So yeah, quite a cool problem. So I hope you enjoyed that. If you enjoyed it, leave a like, feel free to subscribe, and share it with your friends.